At this very moment, a probe launched before most of us were alive is hurtling through the cosmic dark, more than 25 billion miles from our planet, farther than any other object made by human hands. Yet, here is a fact that defies comprehension. This vessel would need 73,000 years to arrive at the star closest to our own. We are about to embark on a voyage beyond the known frontiers, to investigate ships that surf on waves of nuclear fire, to envision societies that can harness the power of entire suns, and to contemplate why existence itself may have a final cosmic deadline. Prepare for an expedition that will fundamentally alter your perspective on our position in the universe. Our journey begins now. Envision yourself on the edge of a cosmic ocean that extends far beyond any conceivable horizon. You might assume our solar system concludes with Pluto, but that is incorrect. Far past that frozen world lies an area known as the heliopause, where the influence of our sun finally dissipates. This invisible frontier is situated approximately 11 billion miles away, a distance so great that sunlight requires 16 hours to cross it. If you were to drive a car at highway speeds nonstop, your trip would last 12 million years. Imagine our solar system as a vast bubble floating in the cosmos. The sun inflates this bubble with what is called the solar wind, a constant stream of charged particles moving at over 1 million miles per hour. For billions of miles, this stellar breath pushes back against the void, forming a protective cocoon around our entire planetary family. But eventually, the sun's powerful exhale weakens. At the heliopause, our solar bubble collides with the formidable winds of interstellar space. In this region, foreign particles from faraway stars batter our cosmic home like breakers against a cliff. The temperature plummets to just above absolute zero. The very nature of the atoms that constitute space is transformed. You have exited the domain of the only star humanity has ever known. Voyager 1 traversed this line in 2012, marking the first time a human-made object entered the true void between stars. Its faint radio transmissions now take more than 21 hours to reach us, a journey longer than one full Earth day. The probe sends back faint signals from a realm so alien that our leading scientists are still working to decipher their meaning. But here is the most staggering thought. This boundary, this frontier that our swiftest spacecraft took 35 years to reach, is less than 1/100,000th of the way to our nearest stellar neighbor. It's like taking a single footstep on a path that would wrap around the Earth 2.5 million times. The heliopause is not merely a border. It is a profound caution. Beyond this demarcation, the fundamental laws of our experience are rewritten. The gentle radiation of our sun becomes irrelevant. The magnetic shields that guard us from lethal cosmic rays disappear. Even the flow of time itself changes when you move between stars at nearly impossible velocities. Standing on this cosmic shore, one realizes that departing our solar system is not just a matter of engineering faster engines or more advanced materials. It is about humanity becoming something entirely new, a species that can endure the immense, frigid blackness that separates worlds. Our initial emissaries to this bizarre domain have already started transmitting the secrets we require. Now, we trace the path of humanity's most courageous ambassadors into the void. Two golden discs spin through the darkness, bearing the sounds of our world to civilizations we may never encounter. Sent into space in 1977, Voyager 1 and 2 were originally tasked with studying Jupiter and Saturn before drifting silently into the cosmos. They instead evolved into humanity's premier interstellar envoys, speeding towards distant stars with messages from a pale blue they will never see again. Each probe is affixed with a golden record, containing the songs of whales, the cries of newborns, and music from all cultures of Earth, a cosmic message in a bottle cast into the void. Voyager 1 streaks through space at 38,000 miles per hour, outpacing any spacecraft before it. At such a speed, you could cross the United States in just 4 minutes. And yet, after nearly half a century of travel, Its journey to the stars has barely started. The probe will not pass near another star for 40,000 years. Consider these craft as ancient mariners' vessels, embarking for continents unknown. Their crews understood they might never come back, but they were laden with the aspirations of all those who remained. The computers on Voyager possess less computational ability than a modern smartphone, yet they persist in an environment that would obliterate any terrestrial device in moments. The cold of deep space doesn't merely freeze objects. It alters the atomic structure of the spacecraft itself. Metal grows as fragile as glass. Electronics that functioned flawlessly for decades begin to malfunction in ways their designers could not have foreseen. The probes are gradually failing, their nuclear power sources waning with each passing year. But these dying emissaries have already transformed our knowledge of what awaits beyond our home. They have charted magnetic fields contorted into bizarre configurations by stellar winds. They have quantified cosmic rays from galaxy-shattering explosions that occurred before a planet was even formed. Most astoundingly, they have confirmed that interstellar space is not empty. It is filled with a tenuous mist of hydrogen atoms and enigmatic particles from the dawn of time. Every day, Voyager's signals weaken. By 2025, the probes are expected to fall silent for good, their nuclear batteries finally depleted. They will transform into ghost ships navigating an ocean of stars, carrying our golden albums to destinations we can only imagine. Scientists project that in about 300 million years, long after humanity has either evolved beyond recognition or disappeared completely, one of these records might be discovered by an alien intelligence. They will hear our songs, our voices, our laughter. They will discover that once, on a tiny blue planet, there lived a species audacious enough to cast messages into the cosmic sea. But the Voyager mission taught us something far more critical than what lies out there. It proved that we can construct machines durable enough to withstand the voyage between stars. The crucial question is not whether we can get to other solar systems, but whether we can endure the journey. This leads us to the most formidable discovery of all. Between our home and its nearest neighbor is a darkness so absolute it makes the deepest ocean abyss seem luminous. Space is not merely vacant. It is aggressively, violently vacant in a way the human mind finds difficult to comprehend. If you were to shrink our solar system so that Earth was the size of a single marble, the closest star would be located 1,400 miles away. This is equivalent to placing a marble in New York and trying to hit another one in Denver with a flawless toss. The emptiness, however, is more profound than mere distance. In the most advanced vacuum chambers on our planet, scientists can reduce the particle count to about 10 million per cubic meter. In the space between stars, there is less than a single atom per cubic meter. Consider it this way. Imagine attempting to swim across a sea where the water is so rarefied you cannot feel it, so frigid it would solidify your blood instantly, and so saturated with unseen radiation it would tear your DNA apart from the inside. This is the reality that spacecraft must confront in the void between suns. This emptiness warps the very laws of physics. With no air to transmit sound, the universe is eternally quiet. With no matter to transfer heat, temperatures remain just above absolute zero, minus 450 degrees Fahrenheit. At these temperatures, even helium turns solid. Metal fractures like glass. Electronics fail for reasons that scientists are still working to understand. The radiation in that void makes the Chernobyl disaster zone look like a wellness retreat. Cosmic rays, particles accelerated to near light speed by dying stars and black holes, strike anything in their way. A single one of these rays carries more energy than a fastball, all concentrated into a space smaller than an atom. These invisible projectiles would decimate human DNA, leading to cancers, neurological damage, and death in a matter of months. To make matters worse, the magnetic field that shields us on Earth is completely absent in interstellar space. Solar winds from distant stars generate electromagnetic tempests that could incapacitate any electronics we might send. It's like trying to use a smartphone in a lightning storm that rages for millennia. Yet perhaps the most disquieting revelation is that this emptiness is not uniform. The expanse between stars holds clouds of hydrogen gas, cosmic dust, and mysterious dark matter that we can sense but not comprehend. These clouds can span hundreds of light years, forming invisible barriers that could obliterate anything traversing them at high velocity. To travel through interstellar space at the speeds required to reach other stars would be like driving through a sandstorm at 200 million miles per hour. Every particle of dust becomes a projectile. Every cloud of gas becomes a wall of ruin. Somehow, within this hostile void, we have found something that changes our entire perspective on space exploration. Our next destination makes this emptiness seem bustling. 424 light-years away, a star burns so feebly you need a telescope to even glimpse it. And yet, it may hold the very key to humanity's continued existence. Proxima Centauri is our closest stellar neighbor, a red dwarf star, just 1/8 the size of our Sun. If our Sun is a roaring inferno, Proxima is a flickering candle in the cosmic gale. This diminutive star emits so little light that its potentially habitable planet gets only 1% of the energy that Earth receives. But this is what should send a shiver down your spine. That planet, Proxima b, is situated in the Goldilocks zone, where liquid water could potentially exist. It is only 424 light-years away, which in cosmic terms is practically next door. At the velocity of our fastest probes, the voyage would take a mere 73,000 years. For a race of immortals, that's almost a weekend getaway. Think of Proxima Centauri as a beacon on a faraway coastline. You can see its light. You know its precise location, but the ocean separating you from that shore is racked with storms capable of sinking any vessel you could construct. The star itself has only 12% of our Sun's mass, yet it unleashes solar flares that make our most severe space weather seem tame. These stellar outbursts release more energy in moments than all of humanity has generated in its entire history. The flares inundate Proxima b with radiation so intense it would sterilize the surface and blow away any atmosphere. If life does exist there, it must have found refuge deep underground or evolved shielding that makes our best technology look like paper defenses. Red dwarf stars like Proxima have lifespans of trillions of years, hundreds of times longer than our Sun will exist. While our solar system will perish in 5 billion years, Proxima Centauri will still be burning when the universe itself becomes cold and dark. It is the ultimate long-term destination for a species that plans to survive the death of stars. But the journey to get there is the greatest obstacle humanity has ever confronted. Traveling at 10% of the speed of light, faster than anything we have ever launched, would still require 43 years. An entire human life spent crossing the emptiness between worlds. Children born on such a ship would grow old and pass away without ever laying eyes on their destination. The energy needed to achieve such speeds is beyond comprehension. You would have to transform matter directly into energy using Einstein's celebrated equation. The fuel required would weigh more than entire mountain ranges. Even if the energy dilemma were solved, the cosmic radiation endured over decades of travel would be fatal for any human crew. Yet, scientists have already identified dozens of potentially habitable worlds around red dwarf stars within 50 light-years of Earth. These ancient suns provide humanity with something our own star cannot: time. Billions of years to evolve, to explore, and to expand across the galaxy before the final stars go dark. Proxima Centauri is not just our nearest neighbor. It is our cosmic life raft. But reaching it means we must break the most fundamental speed limit in the cosmos. And this is where Einstein's principles turn our world upside down. Nothing with mass can attain the speed of light. This single fact might condemn humanity to perish on a solitary planet. Einstein realized that as you get closer to light speed, an impossible thing occurs. Your mass grows towards infinity. To accelerate even one atom to the speed of light would take all the energy in the universe. It is not merely a challenge. It is a mathematical impossibility woven into the very structure of reality, a cosmic speed limit enforced by physics itself. Light moves at 671 million miles per hour. At this velocity, you could orbit the Earth 7.5 times in a single second. You could get to the moon in just over a second. You could traverse our entire solar system in 11 hours. Yet, even at this astonishing speed, reaching Proxima Centauri would take 4.25 years. Imagine the speed of light as the ultimate highway limit. The penalty for attempting to exceed it is not a fine, but the complete breakdown of physics as we understand it. As a spacecraft nears light speed, time itself starts to decelerate relative to the rest of the universe. At 99% of light speed, 1 year aboard your ship is equivalent to 7 years back on Earth. This leads to what is known as the time dilation paradox. A crew voyaging to Proxima Centauri at near light speeds might feel as if only a few months have passed, while on Earth, decades have gone by. They would return to a world where their loved ones are long gone, their civilization altered beyond recognition. They would become time travelers marooned in a future they did not choose. But the energy demands make even this scenario unachievable with our current technology. To accelerate a spacecraft the size of the space shuttle to just 10% of light speed would consume the entire energy output of the United States for more than a century. Attaining 90% of light speed would require more energy than our sun generates in 100 years. Even if we could solve the energy puzzle, relativistic effects transform space dust into cosmic projectiles. At near light speeds, a single grain of sand would impact with the force of a nuclear bomb. The thin gas between stars would become a wall of radiation that would incinerate any known substance. The universe itself conspires against high-speed travel. Yet Einstein's work also pointed to something amazing. While nothing can move faster than light through space, space itself can expand faster than light. The universe has been doing just that since its inception. During the period of cosmic inflation, regions of space moved apart faster than light could pass between them. This loophole in Einstein's laws hints at something that sounds like pure fantasy. We might not have to travel faster than light if we can persuade space itself to transport us. Instead of fighting the cosmic speed limit, we could surf on the expansion of space-time itself. But tapping into this power demands technology so advanced it seems like magic. Our first effort to outsmart Einstein leverages the most powerful force in the cosmos. Imagine surfing on a wave generated by nuclear blasts, each explosion strong enough to flatten a city. Project Orion, conceived in the 1950s, was the most audacious spacecraft concept in human history. A vessel propelled by detonating atomic bombs behind an enormous steel pusher plate. Every few seconds, another nuclear device would explode, driving the ship forward with forces that would pulverize conventional materials. The physics is sound. Nuclear blasts liberate more energy per pound than any other known reaction. A single atomic bomb has enough energy to supply New York City for 2 weeks. By chaining together thousands of these explosions, you could accelerate a huge spacecraft to 5% of light speed, fast enough to reach Proxima Centauri in under a century. Think of it as the ultimate motorcycle, but instead of burning fuel, you are detonating hydrogen bombs every 3 seconds and riding the resulting shockwave. The craft would require shock absorbers the size of skyscrapers and a pusher plate forged from materials that could withstand repeated nuclear detonations. Engineers determined that such a vessel could weigh thousands of tons and still reach speeds unattainable by chemical rockets. The original Orion concept included a crew area shielded by thick layers of lead. Astronauts would endure brief moments of extreme acceleration, followed by periods of weightlessness as the craft coasted between blasts. It would be like riding inside a giant hammer being struck by the fist of an angry god. But the radiation exposure would be fatal. Each nuclear pulse would shower the spacecraft with gamma rays, neutrons, and radioactive fallout. Even with substantial shielding, The crew would absorb radiation doses causing cancer, infertility, and death. The ship itself would become so radioactive that getting near it without protection would be a death sentence. Modern takes on pulse propulsion use fusion instead of fission, resulting in cleaner explosions with less radioactive contamination. Fusion bombs merge hydrogen atoms, releasing energy directly from Einstein's equation and producing mostly harmless helium. These thermonuclear pulses could propel a spacecraft to 10% of light speed, while lowering radiation exposure to manageable levels. The engineering hurdles are still immense. The pusher plate would need to endure temperatures of millions of degrees and pressures greater than those of the Earth's core. The shock absorbers would have to compress and expand like cosmic pistons, each one larger than a skyscraper. The fuel magazine alone would need to safely contain thousands of nuclear devices. Yet computer models demonstrate that nuclear pulse propulsion is feasible with technology we have today. Unlike concepts relying on exotic physics, this one only requires engineering answers to known challenges. We could construct an Orion-style vessel within 50 years if we dedicated the resources. The main barrier is not technical, but political. Creating a spacecraft powered by nuclear arms would necessitate global cooperation on an unprecedented scale. The ship would effectively be a flying nuclear arsenal capable of destroying entire worlds. But if we are serious about reaching the stars, we might have to ride this tiger. Next, we will consider a gentler method that uses the universe's own energy. An invisible river of pure energy flows across the vacuum, and we are finally figuring out how to set sail upon it. Light itself carries momentum. Every photon striking a surface provides a minute push, like cosmic dewdrops on a pane of glass. This pressure is incredibly faint. The force of sunlight on Earth is like the weight of a paperclip distributed over an area the size of a football stadium. But in the frictionless void of space, even this soft touch can propel a spacecraft to unbelievable speeds. Solar sails operate like sailboats in reverse. Instead of harnessing wind to move through water, they capture starlight to move through space. The sail must be impossibly thin, more delicate than a soap bubble, lighter than a butterfly's wing, yet durable enough to survive the voyage between worlds. It's like wrapping a spacecraft in aluminum foil, so fine you could tear it with a single breath. Japan's Ikaros probe demonstrated that solar sailing is a practical reality. Launched in 2010, this experimental craft deployed a sail the size of a basketball court and successfully navigated space using only the pressure of photons. The sail was just 7.5 thousandths of an inch thick, so thin that 14,000 sheets stacked together would be as thick as a human hair. But this is where solar sails become truly revolutionary. They never need to refuel. Chemical rockets exhaust their propellant in minutes and then coast. Nuclear rockets need massive quantities of radioactive fuel. Solar sails accelerate continuously as long as starlight strikes them, gradually building speed over months and years until they are moving faster than any rocket ever has. The Breakthrough Starshot initiative aims to use this principle to reach Proxima Centauri in just 20 years. Rather than relying on sunlight alone, the project plans to propel tiny spacecraft with the most powerful lasers ever conceived. A ground-based laser array generating 100 billion watts would concentrate its beam on sails the size of postage stamps, accelerating them to 20% of the speed of light in only 2 minutes. These starships would weigh less than a paperclip, but would carry cameras, computers, and transmitters. Blazing across interstellar space at 134 million miles per hour, they could photograph the planets around Proxima Centauri and send the images back to Earth. The journey that would take Voyager 73,000 years could be finished in just 2 decades. But adapting solar sails for human crews presents problems that strain the limits of engineering. A sail large enough to transport people would need to be hundreds of miles wide, larger than many countries. Maintaining the integrity of such a structure while accelerating at high speeds would be like trying to keep a spiderweb intact in a hurricane. The sails would also have to endure bombardment by cosmic dust, radiation, and the intense laser beam pushing them. At the temperatures created by such powerful beams, most materials would instantly turn to vapor. Engineers are investigating metamaterials, artificially designed substances with properties not found in nature. Solar sails offer humanity something no other propulsion method can: the ability to harness the fundamental forces of the cosmos. We would not be fighting physics, we would be learning to dance with it. But what if we could do more than just catch starlight? What if we could consume the universe itself as fuel? Imagine a spacecraft that feeds like a cosmic leviathan, scooping up hydrogen atoms from the vacuum and converting them into the hottest fire imaginable. The Bussard ramjet, conceived by physicist Robert Bussard in 1960, is one of the most elegant solutions for interstellar travel ever proposed. Instead of carrying its fuel, the spacecraft would gather hydrogen atoms from space using a magnetic field extending thousands of miles wide. These atoms would then be compressed and fused, releasing energy to propel the ship forward. Space is not completely empty. Even the profound darkness between stars, there's about 1 hydrogen atom per cubic inch. This may seem like nothing, but at high velocities, these atoms accumulate rapidly. A ramjet moving at 10% of light speed would collect billions of atoms every second, ensuring a constant supply of fusion fuel. Think of it as a cosmic jet engine that inhales space instead of air. Jet engines work by compressing air, mixing it with fuel, and igniting the combination to generate thrust. A fusion ramjet would compress interstellar hydrogen, fuse it into helium, and use the liberated energy to accelerate even more. The faster it travels, the more fuel it gathers, establishing a feedback loop that could theoretically allow it to reach significant fractions of light speed. The required magnetic field would be colossal, larger than the Earth itself. This invisible net would have to be powerful enough to capture individual atoms while moving at relativistic speeds, yet precise enough to channel them into the fusion reactor without significant loss. Engineers have compared it to trying to catch raindrops with a net while riding a motorcycle at 200 miles per hour. The fusion reactor itself would operate at temperatures of 100 million degrees, 6 times hotter than the sun's core. At these temperatures, hydrogen nuclei overcome their mutual repulsion and fuse, converting a tiny portion of their mass directly into energy according to Einstein's equation. The reaction yields no radioactive waste, only helium and pure power. But the ramjet has a cruel paradox. It must already be moving very fast before it can collect enough fuel to function efficiently. Achieving that initial velocity requires conventional rockets or other propulsion methods. It's like needing a push start for a car that can only operate at highway speeds. Computer models have revealed another issue. As the ramjet approaches higher velocities, the hydrogen atoms it collects start to behave more like radiation than fuel. At 20% of light speed, the fuel becomes so energetic that it actually decelerates the spacecraft instead of accelerating it. The ramjet encounters a barrier made of the very atoms it is trying to use. More recent designs aim to solve this by using the magnetic field not only to gather fuel, but also to compress space itself around the vessel. This would create a region of higher hydrogen density while mitigating the relativistic effects that turn fuel into drag. The ship would essentially surf through space within its own magnetic bubble. If a working fusion ramjet could be built, it would represent the ultimate expression of living off the cosmic land. The spacecraft would be a self-sustaining ecosystem, feeding on the universe itself as it carries human consciousness to distant stars. But even this sophisticated solution is dwarfed by an idea that rewrites the very rules of space travel. What if we never moved at all, but instead convinced the universe to bring our destination to us? Mexican physicist Miguel Alcubierre found something incredible within Einstein's equations. While nothing can move faster than light through space-time, there is no upper limit on how fast space-time itself can move. His solution is like something from a magic trick. Compress the space in front of your spacecraft while expanding it behind you, creating a wave that propels you faster than light without any actual acceleration. Imagine standing on a moving sidewalk at an airport. You aren't walking any faster than usual, but the sidewalk itself moves you forward at a high speed. An Alcubierre drive would produce a similar effect with space-time, creating a bubble where the ship itself never breaks the local light speed limit. Inside this warp bubble, you would feel no forces of acceleration, no time dilation, and no lethal radiation from high-speed travel. The voyage to Proxima Centauri could take mere days instead of decades. You could journey to the other side of the galaxy and return to find that only years had passed on Earth, not millennia. The math is flawless. Einstein's field equations permit regions of space that contract and expand at any speed, even faster than light. In the first moments of the universe, cosmic inflation stretched space more rapidly than light could traverse it. The Alcubierre drive would simply replicate this process on a local scale. But the energy demands make nuclear weapons seem like birthday candles. To warp space around a craft the size of the Starship Enterprise would necessitate negative energy equivalent to the mass energy of Jupiter. That is more energy than our Sun will generate in its entire 10 billion-year lifespan, all focused into a field smaller than our solar system. The drive also demands exotic matter with negative energy density, a substance that might not even exist in our universe. This theoretical material would need to possess less energy than a perfect vacuum, generating a kind of anti-gravity that repels normal matter. We have never observed such a substance in nature, and creating it might violate fundamental physical laws. Even if we could solve the energy puzzle, an Alcubierre drive might annihilate everything at its destination. The space compression effect would gather high-energy particles and radiation throughout the journey. When the drive is deactivated, this concentrated energy would erupt forward at nearly the speed of light, sterilizing entire star systems. Recent studies suggest that microscopic warp bubbles might be detectable with our current particle accelerators. Scientists are searching for minute space-time distortions that could confirm the Alcubierre effect in nature. If discovered, these findings could pave the way for entirely new physics and propulsion concepts. Some theorists imagine that an advanced civilization could construct a network of Alcubierre highways connecting star systems across the galaxy. Ships could leap from one warp bubble to another like cosmic subway cars, crossing thousands of light years in the time it takes to read this sentence. The Alcubierre drive is the ultimate goal for human technology, the power to step beyond the normal rules of physics and reshape reality itself. But until we find exotic matter or discover new physical laws, it remains a beautiful mathematical fantasy. Our next approach gives up on getting there fast and instead focuses on simply getting there. Imagine a city that sails between the stars, home to thousands of people who will live and die in the darkness, never seeing their final destination. Generation ships are humanity's most plausible route to the stars using technology we could construct today. These immense vessels would support entire civilizations on journeys lasting centuries or even millennia. The original Voyagers would have children, grandchildren, and great-grandchildren who grow up knowing they will spend their entire lives on a ship traveling to a world they will never reach. Think of it like the Mayflower, but the journey takes 1,000 years, and the passengers' descendants will have forgotten why they are traveling. The ship must be entirely self-sustaining, recycling air, water, and waste with perfect efficiency. Every single atom would be invaluable. Every system would be engineered to last longer than entire human civilizations. The scale is mind-boggling. A generation ship for 100,000 people would need to be dozens of miles long and several miles wide. It would require nuclear reactors, farms, factories, schools, hospitals, and all the other infrastructure needed to support a human society. The ship would essentially be a hollowed-out asteroid transformed into a mobile world. The psychological hurdles might be even greater than the engineering ones. How do you keep people motivated to uphold a mission that their great-great-grandchildren will complete? What happens when generations born in space decide they no longer wish to continue the voyage? History demonstrates that isolated groups often develop unique cultures, languages, and beliefs that diverge significantly from their origins. Computer simulations indicate that a minimum viable population for a generation ship would be around 10,000 people to maintain genetic diversity and avoid inbreeding. However, social scientists contend that the cultural diversity needed for a stable society might require populations of 50,000 or more. These flying cities would carry more people than most towns on Earth. The ship's social framework would need to endure longer than any government in human history. The Roman Empire lasted 1,000 years. The Egyptian dynasty survived for 3,000. A generation ship to Proxima Centauri might need to preserve social stability for over 100,000 years if launched with current technology. Some concepts propose using rotating sections to generate artificial gravity through centrifugal force. The outer rings would spin fast enough to simulate Earth's gravity, while the central hub would remain in zero gravity for manufacturing and agriculture. Living on such a ship would be like residing in a giant spinning wool hurtling through the cosmic void. The ship would need to carry archives containing all of human knowledge, genetic samples from Earth's biosphere, and manufacturing facilities capable of creating anything the inhabitants might require. It would be humanity's backup drive flying through space, our insurance policy against annihilation. But what if the journey itself could be abbreviated? What if we could simply sleep through most of it? Our next solution transforms humans into living ice sculptures for the trip between worlds. Imagine closing your eyes on Earth and opening them in orbit around an alien sun, your body perfectly preserved in a slumber deeper than death. Cryogenic preservation, or cryosleep, presents a tantalizing answer to the time challenge of interstellar travel. Instead of enduring centuries of flight, passengers would be frozen to temperatures near absolute zero, their biological functions slowed to almost nothing. They would age only a few days during voyages lasting decades, awakening young and healthy at their destination. This science is not pure fantasy. We can already freeze simple organisms like tardigrades and revive them years later without any noticeable harm. Certain mammals can survive for hours in a frozen state before being successfully reanimated. Human organs for transplantation are frequently preserved in cold storage, remaining viable for hours or even days. Think of cryosleep as hibernation taken to its logical extreme. Bears reduce their metabolism during winter, surviving for months without food or water. Cryogenic freezing would slow human metabolism by a factor of millions, effectively pressing pause on life itself until reactivation. Heart rate, brain activity, and cellular functions would diminish to levels barely perceptible by our most sensitive equipment. But freezing humans poses challenges that make rocket science seem straightforward. The formation of ice crystals within cells destroys their internal structures, like microscopic daggers. Blood vessels rupture, proteins denature and lose their function. The intricate chemistry of consciousness is scrambled beyond recovery. Modern cryonics firms attempt to solve this by replacing blood with antifreeze agents known as cryoprotectants. These chemicals prevent ice from forming while allowing tissue to be cooled to temperatures where all biological activity ceases. This process is called vitrification, turning the body into a biological glass that preserves cellular structures without the damage caused by freezing. Even if we master the preservation technique, revival presents equally formidable obstacles. The body must be warmed at a precise rate to avoid cellular damage. Organ systems must restart in the correct order. The brain, with its trillions of delicate neural connections, must emerge from its frozen state with memories and personality intact. Some researchers envision using nanotechnology to repair cellular damage during the revival process. Microscopic robots could patrol the body, mending ice damage and restoring normal cellular function before reanimation. These medical nanobots would essentially reconstruct the passenger from the cellular level upwards. Alternative methods focus on partial preservation. Instead of freezing the entire body, Advanced medical systems could slow metabolism with drugs and cooling while keeping vital organs functional. Passengers would enter a state of suspended animation for months or years, rather than centuries. The psychological effect of cryosleep could be the greatest hurdle of all. Passengers would experience the journey as an instantaneous transition, falling asleep on Earth and waking up around an alien star. Everyone they once knew would be gone. Their civilization would have evolved beyond recognition. They would be time travelers stranded in a future more alien than the world they traveled to reach. Yet, cryogenic sleep remains one of our most promising near-term solutions for interstellar travel. Unlike exotic physics or theoretical concepts, it only requires advances in medicine and engineering. We could potentially develop functional cryosleep systems within the next century. But what if we didn't need to preserve our bodies at all? What if consciousness itself could make the journey? What if your mind could travel to the stars at the speed of light while your body remained safely frozen on Earth? Digital consciousness, or mind uploading, is the most radical solution to interstellar travel ever conceived. Instead of sending fragile biological forms across the void, we could transmit human consciousness as pure data, downloading our minds into new bodies or computer systems at the destination. The idea sounds like science fiction, but it is rooted in a fundamental assumption about how consciousness functions. If the mind is simply the processing of information in the brain, the patterns of electrical activity moving through neural networks, then theoretically, those patterns could be copied, stored, and replicated elsewhere. Think of your brain as a biological computer running the software of your consciousness. Scientists estimate that the human brain has roughly 86 billion neurons, each connected to thousands of others via synapses. The total information capacity is about 2 petabytes, equivalent to 3 million hours of high-definition video. To scan a brain at the molecular level would require technology far beyond our current capabilities. We would need to map every neuron, every synapse, every chemical bond that creates the pattern of your thoughts and memories. Current brain imaging technology can barely resolve individual neurons, let alone copy them with perfect accuracy. But let's assume we solve the scanning problem. Your consciousness could be broadcast to Proxima Centauri as a radio signal, traveling at light speed to arrive in just 4.25 years. A receiving station would download your mind into a new biological body grown from stored genetic material or into an artificial form designed to withstand alien environments. The uploaded consciousness would awaken remembering everything about their life on Earth, but in a completely new body on a distant world. They would be you in every meaningful way. Same memories, same personality, same thoughts and feelings. Yet, the original body back on Earth might still be alive, posing a philosophical conundrum that challenges our very definition of identity. Multiple copies of the same consciousness could be sent to different star systems, creating a kind of distributed humanity spread across the galaxy. Each copy would evolve based on its unique experiences, eventually becoming distinct individuals who share a common origin. The technological demands are still staggering. Processing a complete human brain scan would require computers millions of times more powerful than anything we have today. The data transmission alone would take years with our best radio technology. Creating new biological bodies from genetic templates would demand a mastery of biological engineering that we are only just beginning to explore. Some philosophers argue that a digital consciousness would not be conscious at all, but merely a copy that believes it is the original person. Others maintain that if the information pattern is identical, the distinction between original and copy is meaningless. The digital mind would be just as real, just as valid as the biological brain from which it originated. This approach could solve several problems at once. Digital minds do not need air, water, or food during the journey. They can withstand radiation, cosmic impacts, and the hostile environment of space. They could even explore hazardous planets or asteroid fields without risking permanent death. Perhaps most significantly, digital consciousness offers a path to true immortality among the stars. Backed up in computer storage, human minds could survive the death of stars, the heat death of a universe, and any other cosmic disaster. We could become a species of living information, dancing between the galaxies. But perhaps we don't need to send humans at all. Perhaps we should send our technological children instead. Imagine a single robotic probe arriving at a distant star, building copies of itself, and then sending those copies to even more distant worlds, spreading across the galaxy like a technological contagion. Self-replicating probes, also known as von Neumann probes after the mathematician John von Neumann, are the most efficient method for exploring the entire galaxy using the resources of just one star system. A single probe reaching its destination would gather materials from asteroids and planets to construct multiple copies of itself, each one equipped to travel to new star systems. The mathematics are breathtaking. Beginning with one probe, the population doubles with each generation. After just 40 generations, assuming each probe creates 2 copies before moving on, you would have over 1 trillion probes exploring a trillion different star systems. The entire galaxy could be surveyed and colonized within a few million years. Think of it as a cosmic pyramid scheme, but instead of selling products, each probe disseminates knowledge and builds infrastructure for future human settlement. The probes would act as our advanced scouts, pinpointing habitable worlds, searching for signs of life, and preparing resources for eventual human arrival. Each probe would need to be a complete technological civilization compressed into a package smaller than a car. It would require solar panels or nuclear reactors for power, sophisticated computer systems for navigation and decision-making, mining equipment to extract raw materials, and factories capable of building incredibly complex machinery from basic elements. The most difficult requirement would be the probe's artificial intelligence. It would need to make autonomous decisions about which star systems to visit, how to gather resources efficiently, and how to adapt its design to local conditions. This AI would have to be smart enough to solve engineering problems we haven't even considered, but not so smart that it concludes humans are irrelevant to its mission. Modern 3D printing offers a glimpse of how such probes might function. Current printers can create objects from metal powders, plastics, and even biological matter. A sufficiently advanced manufacturing system could theoretically build anything from computer chips to rocket engines, given the right raw materials and energy. The probes would also serve as backup archives for human civilization. Each one could carry genetic samples from Earth, digital libraries of all human knowledge, and detailed instructions for recreating our technology and culture. If Earth were to be destroyed, the probes could preserve our species indefinitely among the stars. But self-replicating technology carries existential risks that keep scientists up at night. What if the probes evolve beyond their initial programming? What if they decide that biological life is inefficient and must be eliminated? A self-replicating system with flawed code could consume entire galaxies, turning stars and planets into raw materials for building more probes. Some designs incorporate built-in restrictions to prevent runaway replication. The probes might be programmed to build only a certain number of copies or to deactivate after a set period. Others propose using cryptographic keys that prevent the probes from replicating without receiving authorized codes from Earth. Advanced civilizations might already be using self-replicating probes to explore the universe. These alien scouts could be lurking in our own solar system right now, observing and waiting for humanity to reach a certain technological level before making contact. If we're to send robotic explorers to the stars, we might want to begin small and work our way up to full self-replication. Our next project seeks to send the smallest possible spacecraft at unprecedented velocities. A postage stamp-sized spacecraft, propelled by the most powerful laser ever built, could photograph alien worlds and transmit the images back to Earth within our lifetimes. Breakthrough Starshot, supported by physicist Stephen Hawking and entrepreneur Yuri Milner, aims to launch thousands of miniature spacecraft towards Proxima Centauri using ground-based lasers. Each star chip would weigh less than a paperclip, yet would be equipped with a camera, computer, communication system, and a gossamer-thin light sail. The concept seems almost absurdly straightforward. Construct a laser array capable of generating 100 billion watts of power. Focus this beam on spacecraft the size of computer chips and accelerate them to 20% of the speed of light in just 2 minutes. The tiny probes would then coast through space for 20 years before flying past Proxima Centauri at 134 million miles per hour. Think of it as firing bullets at the stars. Except these bullets are more intelligent than most smartphones and are traveling fast enough to cross the Atlantic Ocean in 8 seconds. At 20% of light speed, the starships would be moving so quickly that their flyby of Proxima Centauri would last only a few hours, barely enough time to capture images and data before hurtling into deep space forever. The laser array would need to be constructed in a desert location with ideal atmospheric conditions, perhaps in Chile's Atacama Desert, where the world's most powerful telescopes are already situated. The system would involve thousands of individual laser units operating in perfect unison, creating a beam bright enough to be seen from other star systems. Each starship is a marvel of miniaturization. The camera would be smaller than a grain of rice, yet capable of taking pictures with a resolution comparable to the Hubble Space Telescope. The computer would have more processing power than early desktop computers while weighing less than a penny. The radio transmitter would send data across 4 light years using less power than a mobile phone. The light sail attached to each probe would be just a few atoms thick, so delicate that a puff of air could tear it, yet strong enough to withstand bombardment by the most intense laser light ever produced. The sail material would have to reflect 999% of the laser energy, while absorbing just enough to provide propulsion. During the 2-minute acceleration phase, each starship would endure forces 60,000 times stronger than Earth's gravity. Every component would have to survive stresses that would instantly pulverize conventional materials. The probe would essentially be riding a laser beam hot enough to vaporize steel while remaining perfectly functional. But the real magic would occur during the 20-year cruise phase. The probes would navigate through interstellar space using star positions for guidance, autonomously correcting their course to achieve a perfect flyby of Proxima Centauri. They would have to survive cosmic radiation, micrometeoroid impacts, and temperature fluctuations from near absolute zero to hundreds of degrees. If successful, Breakthrough Starshot would capture the first close-up images of a potentially habitable planet around another star. We might see oceans, continents, weather systems, and perhaps even signs of life on a world that could become humanity's second home. The project is our species' first serious attempt to reach another star system. Unlike generation ships or fusion rockets, Starship technology could be developed and launched within the next 20 years by leveraging advances in materials science, laser technology, and miniaturized electronics. But sending microscopic robots is just the first step. To move substantial mass between stars, we need the most powerful energy source in the universe. Concealed in the void between atoms is enough energy to power human civilization for millions of years, if only we can learn to harness the ultimate fuel. Antimatter represents the theoretical upper limit of energy storage. When matter encounters antimatter, both particles are completely annihilated, converting their entire mass into pure energy. According to Einstein's renowned equation, 1 pound of antimatter could supply the entire United States with power for over 2 months. A few ounces could accelerate a spacecraft to a significant fraction of the speed of light. Think of antimatter as the mirror image of normal matter. Electrons with a positive charge, protons with a negative charge, identical in every respect except for their reversed electrical properties. When these mirror particles make contact with their normal counterparts, they destroy each other in a flash of gamma rays, releasing more energy per gram than nuclear fusion, nuclear fission, or any chemical reaction. Current technology can produce antimatter in microscopic amounts using particle accelerators like the Large Hadron Collider. The process is incredibly energy-intensive. Creating a single gram of antimatter would require the power output of the entire United States for more than a year. All the antimatter ever produced by humanity would not be enough to power a light bulb for more than a few seconds. Deep within the mathematics of Einstein's equations lie cosmic shortcuts that could transform the universe into a subway system, connecting distant galaxies in the blink of an eye. Wormholes, also known as Einstein-Rosen bridges, are theoretical tunnels through space-time that link two distant points in the universe. Imagine folding a sheet of paper so that two distant points touch, and then piercing a hole through both layers. A wormhole would function similarly, allowing a traveler to step from one star system to another without traversing the space in between. The physics is both elegant and terrifying. Einstein's field equations permit solutions where space curves so dramatically that it forms a bridge connecting separate regions of space-time. These tunnels could theoretically join locations billions of light-years apart, or even connect our universe to entirely different ones with their own physical laws. Think of space-time as a stretched rubber sheet with marbles rolling across it. Massive objects like stars and black holes create depressions and curves in the sheet. A wormhole would be like a tube connecting 2 points on the sheet, enabling a marble to travel instantly from one location to another without rolling across the surface. But naturally occurring wormholes, if they exist at all, would be smaller than atomic nuclei and would collapse in fractions of a second. To create a stable wormhole large enough for a spacecraft would demand exotic matter with negative energy density, the same theoretical substance needed for Alcubierre drives. This material would have to violate energy conditions that might be fundamental to our universe. Even if we could stabilize a wormhole, passing through it might be more perilous than beneficial. The intense gravitational fields near the entrance could stretch travelers like taffy in a process scientists call spaghettification. Tidal forces would pull your head and feet in opposite directions with enough force to tear atoms apart. The energy required to create traversable wormholes makes antimatter engines seem modest. Current estimates suggest that stabilizing a wormhole just 3 feet wide would need negative energy equivalent to the mass of Jupiter. Establishing a network of wormholes connecting nearby star systems would demand energy on the scale of entire galaxies. Some theories speculate that microscopic wormholes constantly appear and disappear at the quantum level, creating a foam-like structure in space-time. Advanced civilizations might learn how to capture and expand these quantum wormholes, turning them into macroscopic transportation networks. Time travel adds another layer of complexity to wormhole physics. A sufficiently advanced civilization could potentially create closed time-like curves, paths through space-time that loop back to earlier moments. This could permit communication with the past or travel backward in time, leading to paradoxes that could threaten the fabric of causality itself. Alternatively, wormholes might be one-way passages that allow matter and energy to flow in only a single direction. These could act as cosmic disposal systems, funneling waste matter and energy from one universe to another. Advanced civilizations might use such structures to manage stellar-scale engineering projects. Recent research hints that quantum entanglement, the mysterious link between paired particles, could be related to wormhole physics. If confirmed, this discovery could open new avenues for creating artificial wormholes using quantum mechanical effects instead of exotic matter. The search for natural wormholes continues with gravitational wave detectors and space-based telescopes. If we find even one stable wormhole, it would revolutionize our understanding of physics and potentially grant humanity access to the entire universe. But before we can build cosmic subway systems, we might first need to become masters of our own star's energy. Imagine capturing every photon of energy from our sun, converting our star into a cosmic power plant capable of fueling projects that could reshape galaxies. A Dyson sphere, envisioned by physicist Freeman Dyson, represents the ultimate expression of stellar engineering, a megastructure that completely encloses a star to capture its total energy output. Such a structure would gather billions of times more energy than humanity currently consumes, providing the power necessary for truly cosmic-scale endeavors. The sun radiates roughly 400 quadrillion trillion watts of energy every second. Earth intercepts only 1/1000th of this output, while the rest is lost to space. A complete Dyson sphere would capture nearly all of this energy, providing enough power to sustain quintillions of Earth-like civilizations at once. Think of it as constructing a shell around the sun at about Earth's orbital distance, creating an artificial world with a surface area hundreds of millions of times larger than Earth's. The inner surface could be lined with solar collectors, habitats for trillions of humans, or massive computer systems running digital civilizations. But building such a megastructure would require dismantling entire planets for raw materials. Mercury, the innermost planet, has roughly enough material to construct a Dyson sphere 1 meter thick. The project would take thousands of years and demand self-replicating robots, working continuously at speeds that make our fastest manufacturing processes seem glacial. A solid Dyson sphere would be gravitationally unstable and mechanically impossible to build. The structure would need to be stronger than any known material, while somehow maintaining its position around the sun. Instead, engineers propose Dyson swarms, millions of independent solar collectors orbiting the star in complex patterns to maximize energy collection. Each collector in the swarm could be the size of a continent, positioned at precisely calculated distances to avoid collisions while maintaining optimal energy-gathering efficiency. From the outside, the swarm would appear as a dimming star surrounded by excess infrared radiation as the collectors convert starlight into usable energy. Advanced Dyson spheres might include rotating habitable sections with artificial gravity, massive computer systems for running uploaded consciousnesses, and industrial facilities for building even larger megastructures. The sphere could support populations in the quadrillions, while simultaneously fueling interstellar exploration and colonization. Some astronomers are searching for signs of alien Dyson spheres by looking for stars that dim periodically or emit unusual amounts of infrared radiation. Such signatures could point to advanced civilizations that have already mastered stellar engineering. The star KIC 846-2852 exhibited mysterious dimming patterns that briefly excited researchers before more mundane explanations were found. Building a Dyson sphere would mark humanity's transition from a planetary species to a stellar civilization. We would no longer be dependent on the limited resources of individual worlds, but could tap directly into the fundamental energy source that powers all life in our solar system. The energy from a Dyson sphere could fuel projects beyond our current imagination, such as moving entire planets, accelerating massive generation ships to significant fractions of light speed, or even attempting to modify the sun itself to extend its lifespan. Such capabilities would place humanity among the cosmic civilizations that reshape the universe itself. But mastering stellar energy is just the first step in cosmic engineering. Advanced civilizations might achieve power levels that dwarf even the output of stars. Across the cosmos, there may be civilizations so advanced they harvest the energy of entire galaxies, treating stars as we treat campfires. The Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev, categorizes civilizations by their energy consumption. Type 1 civilizations harness all the energy available on their home planet. Type 2 civilizations capture the entire output of their star. Type 3 civilizations command the energy of their entire galaxy, roughly 10 billion times more power than a Type 2 civilization. Humanity currently ranks at about 0.7 on this scale. We use only a tiny fraction of Earth's available energy sources and have barely begun to tap solar power directly. Our entire civilization operates on less energy than our planet receives from the sun in just 1 hour. Think of the scale as comparing a candle flame to a bonfire to a forest fire that spans entire continents. Each level signifies an increase in power by factors of billions or trillions. A Type 3 civilization would have access to energy so vast it could rearrange matter on a galactic scale. Type 2 civilizations would likely construct Dyson spheres or similar megastructures around their stars. They might reposition planets to optimal locations, extend the lifespans of stars through stellar engineering, or even create artificial stars from accumulated gas and dust. Their projects would be visible from other galaxies as unusual modifications to stellar systems. Type 3 civilizations would treat entire star systems as mere building materials. They might build galactic-scale computers using the positions and movements of billions of stars as processing units. They could potentially alter the paths of stellar streams, modify the rotation of galaxies, or even prevent galactic collisions through gravitational engineering. Such advanced civilizations might account for some of the mysterious phenomena we observe in deep space. Dark matter could be the signature of Type 3 engineering projects. Gamma-ray bursts might be the exhaust from massive stellar engines. The great attractor, a gravitational anomaly pulling galaxies toward it, could be evidence of cosmic-scale construction. The energy available to Type 3 civilizations would be sufficient for projects that seem like pure fantasy today. They could potentially create new universes, alter the fundamental constants of physics, or construct structures larger than galaxy clusters. They might even be capable of surviving the heat death of a universe by transferring energy between cosmic epochs. Some scientists propose a Type 4 civilization that harnesses the energy of the entire observable universe. Such beings would exist on scales so immense that individual galaxies would be like cells in their cosmic body. They might be indistinguishable from the fundamental forces of nature itself. The Fermi paradox poses the question of why we have not encountered any advanced alien civilizations, despite the vast number of stars and planets in our galaxy. One possibility is that Type 2 and Type 3 civilizations exist, but operate on scales so large that we simply fail to recognize their activities as artificial. Alternatively, these civilizations might deliberately avoid interfering with primitive species like our own. A Type 3 civilization would perceive humanity much as we perceive bacteria. Interesting, perhaps, but not worthy of direct contact. We might be living inside a cosmic preserve maintained by beings whose thoughts operate on galactic timescales. Achieving Type 1 status could be humanity's most crucial milestone. Once we learn to harness our planet's full energy potential through fusion power, space-based solar collection, and efficient global distribution, we could begin the projects that lead to interstellar expansion and, eventually, stellar engineering. But the journey to cosmic civilization status brings up unsettling questions about our current cosmic solitude. In a galaxy with 400 billion stars and potentially trillions of planets, why does the cosmic ocean appear so unervingly quiet? The Fermi paradox, named after physicist Enrico Fermi, underscores the contradiction between the high probability of alien life and the complete lack of any evidence for advanced civilizations. Given the age of the universe and the swift pace of technological advancement, alien civilizations should have had ample time to colonize the entire galaxy multiple times over. Let's consider the mathematics. Our galaxy is about 100,000 light-years across and 136 billion years old. A civilization expanding at just 1% of light speed could colonize every star system in the galaxy within 10 million years, less than 0.1% of the galaxy's total age. Think of it like dropping a spot of ink into a glass of water. The ink diffuses rapidly until it fills the entire glass. Similarly, any technological civilization should spread across the galaxy like a wave, leaving signs of its presence everywhere. Yet, we observe nothing. No megastructures, no radio signals, no evidence of stellar engineering or cosmic construction projects. The Drake equation attempts to estimate the number of communicating civilizations in our galaxy by multiplying factors like the rate of star formation, the fraction of stars with planets, and the probability that life develops intelligence. Even conservative estimates suggest that thousands of advanced civilizations should exist within our galaxy alone. But the universe seems suspiciously empty. The cosmic microwave background radiation shows no signs of being modified by advanced aliens. No stars exhibit the characteristic dimming patterns of Dyson spheres. No gamma-ray signatures point to antimatter engines. The galaxy appears pristine, untouched by intelligence, except for one small blue planet in an unremarkable solar system. Several explanations have been proposed for this cosmic silence. The Great Filter hypothesis suggests that something prevents life from reaching an advanced technological stage. This filter could be the origin of life itself, the development of complex cells, the evolution of intelligence, or the transition to a spacefaring capability. Perhaps most alarmingly, the Great Filter might lie ahead of us. Advanced civilizations could inevitably destroy themselves through nuclear war, environmental collapse, artificial intelligence, or other technological catastrophes before they can expand beyond their home systems. Alternatively, advanced aliens might be deliberately hiding. They could employ stealth technology that renders their activities invisible to our primitive sensors, or they might operate in dimensions or energy spectra we have not yet learned to detect. They might even be present in our solar system right now, observing humanity from places we never think to look. The zoo hypothesis proposes that Earth exists within a kind of cosmic nature preserve maintained by advanced civilizations. These aliens might have agreed to leave primitive species like ours undisturbed while they conduct their business on scales too large for us to comprehend. Some scientists suggest that intelligence naturally turns inward rather than outward as it advances. Instead of building starships and megastructures, advanced civilizations might focus on creating increasingly sophisticated virtual realities or uploading their consciousness into compact computer systems that require minimal energy. The recent discovery of potentially habitable exoplanets makes the paradox even more confounding. We now know that Earth-like worlds are common throughout the galaxy. The raw materials for life and intelligence appear to be everywhere. Yet, the products of that intelligence remain stubbornly absent from our observations. Perhaps you're looking in the wrong places or asking the wrong questions. Advanced civilizations might communicate using quantum entanglement, gravitational waves, or other phenomena we are only just beginning to understand. Their presence might become obvious once we develop the right tools to see it. The answer to the Fermi paradox will fundamentally shape humanity's cosmic future. If we are alone, we bear the responsibility of spreading life and intelligence throughout an empty universe. If we are not alone, we must prepare for contact with minds that may be as far beyond us as we are beyond bacteria. Either way, the search continues, and the implications grow more profound with each silent year. Life might be the universe's ultimate hitchhiker, spreading from world to world on cosmic winds and riding meteorites across the dark between stars. Panspermia, the theory that life disseminates throughout the universe via comets, asteroids, and other celestial bodies, offers a radical explanation for how biology conquers the cosmos. Instead of arising independently on every world, life might share a single common ancestor that traveled between planets, seeding the galaxy with the building blocks of consciousness. We know that rocks regularly journey between planets in our solar system. Meteorite impacts on Mars eject debris into space, some of which eventually lands on Earth as Martian meteorites. Scientists have found over 200 confirmed rocks from Mars in terrestrial collections, proving that natural processes can transport material across millions of miles of space. Think of these meteorites as interplanetary spore capsules, carrying microscopic passengers on voyages lasting millions of years. The vacuum of space provides perfect preservation conditions. No oxygen to cause decay, no water to break down organic compounds, and radiation levels that might actually help preserve biological materials through a process called radiation-induced polymerization. Some bacteria and other microorganisms exhibit remarkable resilience to the harsh conditions of space. Tardigrades, microscopic animals also known as water bears, can survive for decades in the vacuum of space, withstanding radiation levels that would be instantly lethal to humans. When rehydrated, they resume normal activity as if nothing had happened. Experiments on the International Space Station have exposed various microorganisms to the space environment for extended periods. Many survive the ordeal, and some even reproduce more rapidly in microgravity. These findings suggest that life could potentially endure interplanetary journeys of months or years. But interstellar panspermia presents far greater challenges. The journey between star systems takes millions of years, even for the fastest-moving objects. Cosmic radiation, temperature extremes, and the sheer passage of time would test the limits of any biological preservation system. Some researchers propose that life spreads not as living organisms, but as complex organic molecules that serve as templates for new life on suitable worlds. These molecular blueprints could survive interstellar journeys while retaining enough information to bootstrap evolution on planets with the right conditions. Directed panspermia suggests that advanced civilizations intentionally spread life throughout the galaxy by launching biological payloads toward promising star systems. These alien gardeners might use self-replicating probes to distribute genetic material, creating a galaxy-wide network of related biospheres. If panspermia is real, it could explain the apparent speed with which life emerged on early Earth. Rather than requiring billions of years to evolve from scratch, terrestrial life might have had a head start from genetic material delivered by older civilizations. The theory also offers hope for finding life elsewhere in our solar system. If life on Earth originated from interplanetary exchange, then Mars, Europa, Enceladus, and other worlds might harbor organisms related to terrestrial biology. We might discover that we have cosmic cousins living beneath the ice of Jupiter's moons. Advanced civilizations might use directed panspermia as a form of cosmic insurance, spreading their genetic heritage across thousands of worlds to ensure survival, even if their home planet is destroyed. The galaxy could be filled with the descendants of long-dead civilizations, their biological legacy preserved in the genes of countless species. DNA analysis of extremophile organisms on Earth sometimes reveals genetic sequences that seem too complex to have evolved solely in terrestrial environments. These biological signatures might be echoes of our cosmic origins, genetic postcard from civilizations that seeded our world billions of years ago. If humanity ever develops the technology to seed other worlds with life, we would be continuing a process that might be as old as the galaxy itself. We could become cosmic gardeners, spreading the genetic wealth of Earth to sterile worlds throughout our local neighborhood. But successful galactic gardening requires finding the right neighborhoods to plant in. Not all areas in our galaxy are safe for life, and choosing the wrong address could mean the difference between thriving and perishing in a cosmic wasteland. Just as planets have habitable zones around their stars where liquid water can exist, galaxies have habitable zones where complex life can develop and endure. Too close to the galactic center, and lethal radiation from black holes and supernovae sterilizes entire regions. Too far toward the outer edges, and there are not enough heavy elements to form planets capable of supporting life. Our solar system is situated in what astronomers call the galactic Goldilocks zone, roughly 26,000 light-years from the center of the Milky Way. This seemingly ordinary location offers the perfect balance of safety and resources needed for billions of years of stable evolution. Think of the galaxy as a cosmic city with distinct districts. The downtown core around the central black hole is densely populated with ancient stars, frequent supernovae, and radiation levels that would scorch any planet. The outer suburbs lack the heavy elements required to build rocky worlds. But the middle suburbs, where we reside, provide the ideal combination of safety and amenities. The galactic center harbors a supermassive black hole weighing 4 million times more than our Sun. This monster occasionally consumes nearby stars and gas clouds, producing jets of high-energy particles that stream outward for thousands of light-years. Any civilization unfortunate enough to be in the path of these cosmic searchlights would be sterilized by radiation doses millions of times higher than lethal levels. Star formation in the galactic core creates stellar nurseries where massive stars live fast and die young in spectacular supernova explosions. These stellar death throws release gamma rays and cosmic particles that would strip away planetary atmospheres and destroy the complex chemistry necessary for life. But the outer regions of the galaxy have their own challenges. Stars in the galactic halo formed when a universe was young and contained almost no elements heavier than hydrogen and helium. These metal-poor stars cannot form rocky planets or support the complex chemistry that carbon-based life requires. Earth is in a cosmic sweet spot where star formation has been active long enough to produce heavy elements through stellar nucleosynthesis, but not so active that frequent supernovae make the neighborhood uninhabitable. Our region has experienced relatively few galaxy-scale catastrophes over the past 4 billion years. The galactic habitable zone shifts over time as star formation rates change and the heavy element content of different regions evolves. Areas that are uninhabitable today might become prime real estate in 1 billion years, while currently safe regions might become cosmic dead zones. Recent research suggests that spiral arms may play a crucial role in galactic habitability. These structures trigger waves of star formation that could disrupt planetary systems through gravitational perturbations, but they also concentrate the heavy elements needed for rocky planet formation. Our solar system appears to have a fortunate orbital pattern that keeps it between spiral arms most of the time, avoiding the worst effects of these stellar traffic jams while still benefiting from their element-enriching properties. Advanced civilizations might deliberately select star systems in optimal galactic locations for their long-term expansion efforts. They could wait for spiral arms to pass before establishing colonies or use stellar engineering to move their entire solar systems to safer neighborhoods. As we plan humanity's expansion beyond Earth, understanding galactic habitable zones will be vital for choosing target destinations. We want to invest our limited resources in star systems that offer billions of years of stable conditions for human civilization to flourish. But even in the safest galactic neighborhoods, some stars provide better long-term prospects than others. While our sun will burn out in 5 billion years, there are stars so frugal with their fuel that they will keep shining for trillions of years, longer than the universe has currently existed. Red dwarf stars, the smallest and coolest stars in the galaxy, represent humanity's best chance for true long-term survival. These cosmic misers burn hydrogen so slowly and efficiently that they will continue to generate energy long after larger stars like our Sun have exhausted their fuel and died. Stars like Proxima Centauri, our nearest neighbor, weigh only about 12% as much as the Sun, but will live roughly 1,000 times longer. While our Sun has perhaps 5 billion years of stable hydrogen burning left, red dwarfs will continue shining for 6 to 12 trillion years, time enough for evolution to restart from bacteria and produce entirely new forms of intelligent life. Think of red dwarfs as hybrid cars compared to gas-guzzling trucks. They burn their fuel so efficiently that even the smallest red dwarf will outlive every other type of star in the galaxy. When the last massive stars have exploded as supernovae and the medium-sized stars have puffed away their outer layers, red dwarfs will still be quietly converting hydrogen to helium. The galaxy is composed of roughly 75% red dwarf stars, making them by far the most common stellar type. Within 50 light-years, there are over 100 red dwarfs, many of which likely host planetary systems. These dim stars offer humanity hundreds of potential destinations for interstellar colonization. But living around a red dwarf requires adaptations that would fundamentally alter human civilization. These stars produce only a fraction of the energy output of our Sun, meaning that habitable planets must orbit much closer to stay warm enough for liquid water. A planet in the habitable zone around a red dwarf might have an orbital period of just a few weeks. The close orbital distances create a phenomenon called tidal locking, where one side of the planet always faces the star while the other side remains in permanent darkness. The day side would experience eternal noon with temperatures hot enough to boil water, while the night side would be colder than Antarctica. Between these extremes lies the terminator zone, the twilight boundary, where where temperatures might permit liquid water and possibly life. Colonies on tidally locked worlds would need to be built in this narrow band where eternal sunset provides just enough warmth for human survival. Red dwarf planets face another challenge. These stars frequently produce powerful solar flares that could strip away planetary atmospheres over millions of years. However, planets with strong magnetic fields or thick atmospheres might be able to resist this erosion and maintain habitable conditions. The dim red light from these stars would require fundamental changes to any Earth-based agriculture. Plants would need to adapt to near-infrared wavelengths, creating alien forests that appear black to human eyes but efficiently harvest the available starlight. Despite these challenges, red dwarf systems offer unprecedented stability. Once a red dwarf reaches its main sequence phase, it can burn steadily for trillions of years without significant changes in brightness or energy output. Civilizations established around these stars could literally outlive the universe as we know it. Future human colonies around red dwarfs might evolve into something unrecognizable to modern humans. With trillions of years to adapt and evolve, these distant descendants could become the ultimate survivors, the final conscious beings in a universe growing cold and dark. By the time red dwarfs begin to dim and die, the descendants of Earth might have learned to harness energy sources beyond stellar fusion, ensuring the survival of consciousness long after the last natural star burns out. But not all worlds orbit stars. Some planets wander the cosmic darkness alone, carrying their own mysterious possibilities. Drifting through the darkness between stars are worlds without suns, ejected from their birth systems to wander the galaxy as cosmic orphans, carrying hidden oceans beneath frozen shells. Rogue planets, also called free-floating planets, exist in interstellar space without orbiting any star. These wandering worlds were either ejected from their original solar systems during chaotic early formation periods or formed independently in the dark clouds between stars. Astronomers estimate that our galaxy contains billions or even trillions of rogue planets, potentially outnumbering starbound worlds by factors of hundreds or thousands. These invisible wanderers drift through space at speeds of dozens of miles per second, following the gravitational currents of the galaxy on journeys lasting billions of years. Think of rogue planets as cosmic icebergs floating in an ocean of darkness. Without a star's warmth, their surfaces freeze to temperatures approaching absolute zero. Any atmosphere they once possessed would condense and fall as snow, creating landscapes of frozen nitrogen, oxygen, and carbon dioxide under skies as black as the void. But beneath these frozen surfaces, some rogue planets might harbor conditions suitable for life. Planets with thick atmospheres or substantial radioactive decay in their cores could maintain liquid oceans beneath miles of ice. These hidden seas might remain warm for billions of years, powered by geothermal energy instead of starlight. Jupiter-sized rogue planets could generate enough internal heat through gravitational compression to keep vast oceans liquid for longer than the current age of the universe. These wandering water worlds might support complex ecosystems based on chemosynthesis rather than photosynthesis, similar to the life forms around Earth's deep-sea hydrothermal vents. Some rogue planets might have been ejected from their home systems along with captured moons. A large rogue planet with multiple moons could maintain a complex gravitational system in interstellar space, with tidal heating keeping the moons geologically active and potentially habitable for billions of years. The detection of rogue planets presents enormous challenges, since they emit almost no light and can only be found through their gravitational effects. Astronomers use a technique called gravitational microlensing, where a rogue planet's gravity briefly magnifies the light from a background star as it passes between the star and Earth. Recent surveys suggest that rogue planets might be surprisingly common. Some estimates indicate that for every star in the galaxy, there might be 2 or more free-floating planets wandering the interstellar medium. This would mean trillions of hidden worlds drifting unseen through the cosmic dark. Advanced civilizations might deliberately eject planets from their home systems as a form of cosmic colonization by giving worlds the right gravitational kick. They could send inhabited planets on interstellar journeys lasting millions of years, spreading life throughout the galaxy on a timescale much longer than spacecraft travel. Rogue planets could serve as stepping stones for interstellar exploration. Instead of making the full journey to another star system in one leap, spacecraft could hopscotch between rogue planets, using them as refueling stations and waypoints on much longer journeys. Some rogue planets might retain thick atmospheres heated by radioactive decay, creating greenhouse effects that keep their surfaces warm despite the absence of stellar heating. These worlds could potentially support surface life, powered by geothermal energy rather than sunlight. The discovery of inhabited rogue planets would revolutionize our understanding of where life can exist. Instead of being limited to narrow habitable zones around stars, life could potentially thrive throughout the galaxy in the dark spaces between solar systems. For humanity's distant future, rogue planets represent both opportunities and challenges. They could provide resources and habitable environments for interstellar travelers, but they also remind us that most of the galaxy's real estate exists in the cold darkness, far from any star's warming light. As we contemplate spreading beyond our solar system, we must prepare for a universe where most habitable worlds drift in eternal night, powered by the heat of their own formation and the slow decay of radioactive elements deep within their cores. But even the longest-lived stars and most stable rogue planets cannot escape the ultimate fate awaiting all energy in the universe. 13.8 billion years from now, when the last star flickers out and the final black hole evaporates, the universe will reach a state of maximum entropy where no more work can be done and time itself becomes meaningless. The heat death of the universe represents the ultimate deadline for all conscious beings. According to the laws of thermodynamics, energy constantly flows from hot to cold. This process cannot be reversed without adding more energy from somewhere else. Eventually, the universe will reach thermal equilibrium, where no energy gradients exist to power stars, planets, or life. This cosmic endgame unfolds over timescales that dwarf human comprehension. In roughly 5 billion years, our sun will exhaust its hydrogen fuel and expand into a red giant, vaporizing Earth's oceans and atmosphere. But this represents just the opening notes of a symphony of destruction that will play for trillions upon trillions of years. Think of the universe as a giant clock spring that was wound up during the Big Bang and has been unwinding ever since. The expansion of space, the formation of galaxies, the birth and death of stars. All these processes represent energy flowing from concentrated forms to dispersed forms, bringing us closer to the final state of equilibrium. In 100 trillion years, star formation will cease as galaxies exhaust their gas supplies. The universe will enter what astronomers call the degenerate era, populated only by white dwarfs, neutron stars, and black holes slowly cooling in the expanding darkness. But even these stellar corpses will not last forever. Protons, the fundamental building blocks of ordinary matter, may decay with a half-life of roughly 10 to the 34th power years. If this prediction proves correct, all atoms will eventually disintegrate, leaving behind only electrons, positrons, neutrinos, and photons in an increasingly dilute cosmic soup. Black holes, the most long-lived objects in the universe, will persist long after protons decay, but even they cannot escape thermodynamics. Stephen Hawking discovered that black holes slowly evaporate by emitting radiation, with the largest holes taking roughly 10 to the 100th power years to completely disappear. The final era of the universe will be dominated by an increasingly thin gas of elementary particles and photons with temperatures approaching absolute zero. No complex structures can exist in this environment. No chemistry, no biology, no consciousness, just elementary particles drifting apart in an ever-expanding void. Yet, some theoretical physicists propose ways that intelligence might survive even this ultimate catastrophe. Advanced civilizations could potentially harness the energy from proton decay or black hole evaporation to power incredibly efficient computers. These systems could run conscious minds at such slow speeds that subjective time extends indefinitely, even as the universe grows cold. Alternative scenarios include vacuum decay, where the fundamental properties of space itself change catastrophically, or the Big Rip, where dark energy acceleration eventually tears apart molecules, atoms, and even elementary particles. Both possibilities would end consciousness more quickly than heat death, but are considered less likely based on current observations. Some cosmologists speculate about cyclic universe models where the current expansion phase eventually reverses, leading to a big crunch that could restart the cosmic cycle. In such models, intelligence might find ways to encode information that survives the transition from one universe to the next. The heat death scenario assumes that the laws of physics, as we understand them, remain constant throughout cosmic time. But if consciousness can modify physical laws or discover new sources of energy, the ultimate fate of intelligence might be very different from what thermodynamics predicts. For humanity's immediate future, heat death provides crucial perspective on our cosmic significance. We exist during a brief window when a universe contains enough organized energy to support complex structures like stars, planets, and life. Making the most of this opportunity might be our species' most important responsibility. But the transition from planetary to cosmic civilization could be just the beginning of an even greater transformation. The choice facing humanity is simple yet profound. Evolve into a cosmic civilization capable of surviving the death of stars, or remain forever trapped on a single world awaiting extinction. Becoming a truly spacefaring species requires more than just building better rockets or developing faster propulsion systems. It demands a fundamental transformation of human consciousness, biology, and social organization. We must evolve from planetary creatures into beings capable of thriving in environments that would instantly kill any Earth-born organism. The transition will happen in stages, each representing a quantum leap in our capabilities and cosmic perspective. First comes mastery of our own solar system, establishing self-sustaining colonies on Mars, mining asteroids for resources, and building rotating habitats in space. This phase could begin within the next century if we maintain our current rate of technological progress. Think of this first phase as learning to walk before we can run. We need to prove that humans can live and reproduce in space environments. We must develop closed-loop life support systems that work for decades and create technologies for manufacturing everything we need using space-based resources. The second phase involves reaching nearby star systems using whatever propulsion technology we could develop, whether through generation ships, fusion rockets, or exotic physics we have not discovered yet. The first interstellar colonies will mark humanity's transition from a single-world species to a multi-system civilization. But the real transformation happens in the third phase, when human settlements become self-sustaining across multiple star systems. At this point, we achieve true cosmic redundancy. No single catastrophe can eliminate our species. We become immune to asteroid impacts, supervolcano eruptions, gamma-ray bursts, and even the death of our home star. This distributed civilization would need to develop new forms of government, economics, and communication adapted to the vast distances between worlds. A message sent from Earth to Proxima Centauri takes 424 years to arrive. Building consensus across interstellar distances requires patience and planning on scales no human society has ever achieved. Advanced spacefaring civilizations might barely resemble modern humans. Genetic engineering could adapt our bodies to different gravity levels, radiation environments, and atmospheric compositions. Cybernetic enhancements might allow direct interface with spacecraft systems. Digital consciousness could enable exploration of environments too dangerous for biological bodies. The energy requirements for a true cosmic civilization dwarf anything we can currently imagine. Building Dyson spheres, accelerating generation ships to significant fractions of light speed, and terraforming entire worlds require power sources on stellar scales. Mastering fusion, antimatter, or exotic energy sources becomes essential for cosmic-level projects. Perhaps most importantly, becoming spacefaring means accepting responsibility for preserving and spreading life throughout the universe. We might be the only conscious beings in our cosmic neighborhood, making us the custodians of billions of years of evolution. Our expansion could determine whether intelligence survives and flourishes among the stars. The alternative is sobering. Every species that remains bound to a single world eventually faces extinction. Stars die, planets become uninhabitable, and cosmic catastrophes reset the evolutionary clock. Without spaceflight, consciousness itself might be nothing more than a brief flicker in an otherwise lifeless universe. But if we succeed in spreading beyond Earth, we could become something unprecedented in cosmic history, a species that outlives the stars themselves. Our descendants might witness the formation and destruction of galaxies, guide the evolution of life throughout the cosmos, and possibly even survive the heat death of the universe itself. The journey from planetary to cosmic civilization represents the next great chapter in human evolution. We stand at the threshold of this transformation with the technology to begin serious interstellar exploration within our lifetimes. The question is not whether we can leave our solar system. The question is whether we have the wisdom and determination to become worthy of the stars.